Okay, so here's our last section. So we're just going to retouch on antibiotic resistance and then look at our case study for reducing waste, which is going to look at the synthesis of Tamiflu. So we talked about antibiotic resistance when we talked about penicillin and the way that antibiotics work. Primarily our concerns with these are the extensive use of broad-spectrum antibiotics, ones that will wipe out larger populations of bacteria and things like that. And not targeted treatments. So this has generally led to and promoted the genetic mutation and proliferation of antibiotic resistance through bacterial strains. So the majority of antibiotic released into our environment are generally not ones that have been used for the treatment of bacteria in humans. These come from aquaculture, so the farming of fish and different aquatic environments like that, as well as the treatment of household pets when people are disposing of them poorly and things like that. Also, we have a wide use of antibiotics used in what we call prophylactic treatments, so being fed to livestock and things like that so that they won't get sick in the first place. Pest control through the use of agriculture using pesticides and herbicides and antibiotics as well in the growing of plants. Sanitizers and cleaning products and toiletries, so antibacterial agents and those which are particularly prevalent in modern households, as well as the sterilization and cultural section in the research industry. So looking at antibiotic resistant bacteria in research, if they are not disposed of properly, then we can be spreading resistant bacteria through our environment. And of course, improper drug disposal. So if you don't take your antibiotics as prescribed for as long and finish the entire course, then you may have some left over. They may become expired, and then if you just throw them in the bin, those are then going to go into landfill and will filter through into our water table and things like that. So after that, we have Tamiflu. So Tamiflu is the antiviral that we looked at earlier. It's manufactured from the starting material shikimic acid, or its salt, which is this structure here. Okay, so it's a semi-synthetic in that we use a precursor that is extracted from natural products and then build on that to make the final drug. It is present in low concentration in a large number of plants, but for industry, the favored is star anise, which you may have seen as it in cooking because it's a popular spice, or Chinese five spice. Okay, so when we extract this, it involves a lengthy chemical process using a number of solvents, and we don't get very, very high yields, okay? So we're talking about large amounts of solvents and waste for not a very high yield of our starting material. When we had particularly bad outbreaks of influenza, the high demand for Tamiflu meant that we had a restricted supply because of this low yield and the time it takes to extract it. So this made it a particularly good candidate for looking at ways to improve its synthesis. So because there was high demand and limited supply, alternatives were looked at for extracting the precursor. And the key things that they've looked at here are green chemical principles, trying to reduce waste, increase yield, and things like that. So now what they look at doing is they produce the precursor by the fermentation of genetically engineered bacteria, which has been patented by Roche Pharmaceuticals. So they use bacteria to grow up this particular precursor. So usually it will probably be using plasmid DNA, which has been inserted, and getting the bacteria to express this compound as they grow. The other way that they do it is from harvesting from the pine needles of pine trees, much like we talked about with Taxol. So different pine tree, but now looking at the needles, it gives low yield, but it's sustainable because the needles are rapidly regrown and can be harvested without harming the tree. And then the other one is using an Indian sweet gum tree which you can get the precursor from there. So there's a number of natural alternatives that we're using for this, which whilst still most of them will have low yields other than the bacteria and things like that, they are more sustainable and renewable than the approaches we've seen before. Okay, so these are some example questions, and on the next slide has the answers for you, just on how these might come up. These are from the textbook. You should have a look at these and then look at the mark schemes very carefully as well, particular with the types of waste and the points that you should be making. There'll be some other questions up online for you to tackle as well, but that's it. That is the end of the standard level content for our option. Good luck, and remember that the test will be in the first week back.